Usually when you talk about like a medical diagnosis, there is this underlying expectation of precision.
Oh, absolutely. It feels like engineering.
Right. You break your arm, you go to the clinic, the x-ray shows that jagged white line on the black film, and the doctor just, points a pen at it and says, well, there it is, right there.
Yeah, it's entirely binary. I mean, the fracture exists in physical space, and our tools capture it perfectly.
Exactly. Broken or not broken. It's a clean, undeniable fact. We love things to be visible like that. We want them categorized, put into a neat little box so we can fix them. But then, you look at something you probably used an hour ago.
Right.
Imagine you're sitting at your desk right now. You open up ChatGPT or Claude or whichever conversational assistant you prefer. You type out a prompt, and it replies. But the reply isn't quite right, so you correct it.
And the machine apologizes to you.
Yeah. It apologizes, it adjusts its tone, and gives you a much better answer.
And in that moment, I mean, the user experience is incredibly persuasive.
Persuasive is an understatement. It feels intuitively, undeniably like that machine is learning from you in real time.
Oh, for sure.
It feels like you are sitting across from this dynamic, fluid intelligence that's like actively wiring itself to your preferences as you speak. But the entire premise of today's deep dive is built on a rather shocking truth about that exact interaction.
The frozen brain.
Right. That intelligence, its brain is completely frozen. It isn't learning a single thing from you.
Yeah, when you are chatting with a deployed model, its underlying mathematical structure is locked in amber.
Locked in amber, I love that.
Not one single parameter, not a single decimal point of its core knowledge is changing based on your conversation.
And that illusion, the massive gap between what we feel the system is doing and what is mathematically happening under the hood is exactly what we're unpacking today. So welcome to this deep dive. If you've ever wondered what is actually happening inside these massive neural networks, well, you are in the right place.
Yeah, and today's stack of sources is just phenomenal.
It really is. We are looking at these dense, up-to-the-minute 2025 and 2026 technical reports, philosophical essays, and global policy documents about how these large language models actually process reality.
Right, and to set the baseline here, we have to completely discard the way we naturally think about memory and learning.
Toss it right out.
Exactly. These models, they do not store facts like a relational database. It's not like a query pulls up a specific row and column. And they certainly don't learn like humans do.
So what are they?
They are, at their core, statistical pattern compressors. They adjust billions of numerical weights through this mathematical process called gradient descent.
Okay, let me pause you right there, because gradient descent is a term that gets thrown around constantly, but we rarely actually visualize it.
True. So imagine you're standing on the side of a massive rolling mountain range, but you are blindfolded.
Okay, blindfolded on a mountain.
Got it. Your only goal is to find the absolute lowest point in the valley. But you can't see the valley, so you just feel the slope of the ground beneath your feet.
Right, you're just feeling around.
Yeah, if the ground slopes downward to your left, you take a step to the left.
So the model is basically just feeling around for the downward slope. But what is the valley in this scenario? What is it looking for?
The valley represents an error rate. Specifically, the error in predicting the very next word in a sequence.
Yeah, okay.
The model takes a guess at the next word, compares its guess to the actual correct word in the training data, and calculates how wrong it was.
And that wrongness is the altitude on our mountain.
Exactly.
Yeah.
So the model takes a mathematical step, adjusting its internal billions of dials to walk slightly downhill, which reduces that error. And it does this trillions of times.
Trillions. The analogy I kept coming back to while reading our stack of sources is that imagine a master chef, but this chef has never actually tasted a single ingredient in their entire life.
No sense of taste at all.
Right. They have no tongue and no sense of smell, but they have memorized a billion recipes. So through pure statistical correlation, they know that salt usually appears near potatoes and, basil usually appears near tomatoes.
Right, they can map it out.
Exactly. They can output a Michelin star recipe on command, but they have zero concept of what flavor actually is.
That captures the mechanical reality perfectly, I think. The chef has compressed the statistical relationships of ingredients without any actual physical grounding in the act of eating.
So the question becomes, how do we get from raw ingredients, which in this case is just unstructured, chaotic internet text, to that Michelin star dish, which is the incredible, eloquent assistant on your phone?
Well, before a neural network can predict text, it needs to be able to read it.
Right.
But neural networks only understand numbers. They do not understand the letter A or the word apple.
So they just see discrete integer tokens.
Yes. Bridging the gap between the chaotic nuance of human language and the rigid structure of machine mathematics requires a translation layer.
And we call this tokenization.
Right. And modern systems rely on a specific algorithm called byte pair encoding, or BPE.
I was absolutely fascinated to learn from the sources that BPE wasn't even invented for artificial intelligence.
No, not at all.
It was a data compression algorithm from like 1994.
Yeah, the AI industry repurposed it because it solves a very specific information theoretic problem. But let's look at how it operates at the bedrock level.
Okay, let's dig in.
Modern systems use byte-level BPE. They don't start by looking at letters or words. They start by looking at the 256 fundamental byte values.
Like the raw computer bytes.
Literally the hexadecimal values from 0x00 to 0xFF that computers use to store any data.
But why start all the way down at the raw bytes? I mean, why not just start with the alphabet?
Because if you start with the English alphabet, your model instantly breaks the moment it encounters something outside that alphabet.
Oh, right.
Think about it. What happens when a user inputs a Japanese kanji character, or a string of Arabic text, or, an entirely new emoji that was just added to smartphones last week?
It wouldn't know what to do.
Right. If the model hasn't seen it, you get an out-of-vocabulary failure. The model essentially panics.
It just throws its hands up.
Yeah, but by starting at the raw byte level, you guarantee that the model can process literally anything, because every piece of digital text, no matter how obscure, eventually breaks down into those 256 bytes.
Okay, so it starts with these individual bytes. Walk me through a mental simulation here. Say I feed it the word unbelievable. What is the algorithm actually doing?
So initially, the algorithm scans your entire training corpus terabytes of text. It looks at the individual bytes and asks which two adjacent bytes appear together most frequently.
Okay.
Let's say it finds that the byte for T and the byte for H are constantly next to each other. It merges them into a brand new single subword token 3.
It just squished them together to save space.
Precisely. Then it scans the text again. Maybe it notices that he frequently follows the. It merges those into the.
And it just keeps doing this.
Iteratively, yes. Thousands and thousands of times. Early merges might combine common letters into syllables like un or bell, but eventually it builds entire common words like apple or house into single tokens.
Until it hits a limit. The sources mention the target vocabulary size is usually somewhere between 32,000 and 200,000 unique tokens, but choosing that exact number isn't arbitrary, right? There's a massive mathematical trade-off happening here.
Oh, a huge one. It dictates the computational efficiency of the entire multi-million-dollar training run.
Let's explore the two extremes of that trade-off.
Sure. Suppose you choose a very small vocabulary, say only 10,000 tokens. The algorithm won't have enough space to store whole words, so a word like unbelievable might get chopped into 5 separate tokens. Un, bel, eve, ob, lef.
Which means reading a single sentence suddenly generates a massive sequence of tokens.
And that is a critical problem because the core mechanism of the model, which we'll discuss shortly, scales quadratically. As the sequence of tokens gets longer, the computational cost doesn't just double, it squares. A small vocabulary creates incredibly long sequences, which basically bogs down the entire supercomputer.
So intuitively, you'd think, well, just make the vocabulary huge, give it 1,000,000 tokens. That way, almost every word is a single token, sequences stay really short, and the computer runs super fast. What is stopping them from doing that?
The memory wall. Every single token in that vocabulary requires its own dedicated row of parameters in the model's embedding matrix.
Oh, I see.
Yeah, you have a vocabulary of 1,000,000 tokens. You need 1,000,000 rows of incredibly dense, high-dimensional numbers just to define them. This consumes an exorbitant amount of GPU memory.
So you run out of RAM.
Exactly. Furthermore, if you have 1,000,000 tokens, some of them are going to be extremely rare words. If a rare token only appears twice in your entire training data, the model's gradient descent won't have enough information to adjust its weights properly. It'll just be a poorly learned token.
So it's this incredibly tightrope walk. You need a vocabulary large enough to compress text efficiently, but small enough to fit in VRAM and ensure every token gets enough training repetition.
Exactly. And the modern tokenizers have evolved even further to enforce logic on this compression. The 2025 and 2026 reports heavily feature regular expression pre-splitting.
I noticed that, but why do we need regular expressions if the byte merging works so well?
Because statistical merging is blind.
What do you mean?
If you just let the BPE algorithm merge the most frequent pairs based purely on statistics, it might notice that the end of a sentence often looks like word period space.
Okay.
It might decide to merge the last few letters of a word, a punctuation mark, and a space into a single bizarre token.
Which destroys the grammatical logic of the sentence.
Exactly the problem.
Ah.
Modern tokenizers use regular expressions, which are essentially hard-coded search patterns, to chop the text into logical structural categories first.
Oh, so it forces the algorithm to separate words from punctuation and letters from numbers before the statistical merging even begins.
Right. This ensures that tokens respect fundamental linguistic boundaries.
It's like breaking human language down into universal Lego bricks. You want clean bricks that snap together predictably, not, weird melted chunks of plastic.
That's a great way to put it.
But I want to pause and look at the real-world fallout of this for you, the listener, especially if you are a software developer building an app. The sources highlight a major friction point here. Companies like OpenAI, Meta, and Google all use slightly different proprietary tokenizers.
They do. They all have slightly different vocabulary sizes and slightly different pre-splitting rules.
Which means if I am a developer and I send the exact same paragraph of text to two different APIs, one might charge me for 100 tokens and the other might charge me for 130 tokens, purely based on how their specific BPE algorithm decided to slice up my words.
Yep.
That is a massive hidden cost variance.
It is. It forces developers into a sort of algorithmic arbitrage. You have to evaluate not just the intelligence of the model, but the compression efficiency of its specific tokenizer against the type of data you process.
Okay, so we have taken the raw, chaotic text, chopped it logically via regular expressions, and compressed it iteratively into numerical tokens. We have our fuel. Now, that fuel enters the engine, the transformer architecture.
The famous transformer.
Right. Now, anyone who has casually read about AI has probably heard of the famous 2017 Google paper, Attention is All You Need.
The paper that essentially launched the modern generative AI era.
Exactly. But the sources we are looking at are from 2025 and 2026. The state of the art has evolved significantly. But let's start with the core mechanism that remained, self-attention. How does the model actually figure out what these numerical tokens mean in context?
Well, when the integer tokens enter the network, they are immediately mapped to dense vectors. We call these embeddings. Imagine each word is now a coordinate in a multidimensional space.
Okay, they're on a map.
The self-attention mechanism then takes over. For every single token in a sequence, it computes 3 distinct mathematical projections, a query, a key, and a value.
Q, K, and V. I always struggled to conceptualize this until I read a specific analogy.
It can be dense, yeah. But the query is essentially what the token is looking for. The key is what the token possesses or represents. And the value is the actual underlying information it contains.
Let me try the analogy here. Imagine you're